Our last lesson, we looked at one definition saying work was the change of energy. So what we're going to look at today is what happens when we do have different types of energy that change from one form to the other. So the first thing we're going to start with is potential energy. And there's lots of types of potential energy. There could be chemical potential energy, there could be elastic potential, but the one we're going to only work with for our calculations is gravitational potential energy. So that means we have some sort of object, it's a certain distance above ground, and we're going to have some sort of potential energy for that. So let's suppose we have a 2 kilogram object and it's 5 meters above ground. So if it's being held there, it's got the potential to fall, and then it'll turn into a moving kinetic energy. So what we want to do is we want to be able to figure out what that energy is at that height or any other particular height. So our formula that we use for potential energy is, and we use a little p to know which one it is, so we use potential energy, it's mass times gravity times height, which is just a modification of work equals force times distance. Right? Force was mass times acceleration, so in this case the acceleration is gravity, and our height would be our distance. So mass times gravity times height. So it's an easy calculation, so in this case our potential would be 2 times 9.81 times 5, which would give us 98.1 joules. So that means that object has 98.1 joules of potential energy. What would happen if that object wasn't above the ground? Let's suppose there was some sort of desk or something in the way. So let's suppose we have some sort of desk, and that desk is 1 meter tall. So now in this case, this 2 kilogram object's only going to fall, but it's only going to fall down 4 meters instead of the 5 meters. So we would redo this calculation the same way, except we would only use 4 for our height. Okay, so you got to be careful what's it relative to. So in this case, we sort of imagine the desk height being the ground, and then instead of the ground being the bottom, we kind of consider the desk height, so it's really only actually falling 4 meters. So that's a pretty easy concept there. And what happens is, because our numbers are sort of changing as we go, you can see that as the object falls, our height would be less and less, therefore we're going to have less and less potential as it falls. So something right at the ground, if we have a height of 0, our potential energy would be 0, because mass times 9.81 times 0 would give us 0. The other type of energy that we're going to work with is kinetic. And kinetic energy is basically energy when something is moving. So as long as it's moving, it's going to have kinetic energy. And the formula we use is 1/2 mv squared. Okay, so that's a pretty easy calculation as well. So for example, let's suppose we look at a 2 kilogram object, and suppose it's moving at 10 meters per second. So our kinetic energy would be 1/2 times 2 times 10 squared. So we would actually get 100 joules for our answer for that one. So kinetic energy is pretty easy. Quite often you're going to get questions where they'll be given to you in kilometers per hour, so you're going to have to convert it back to meters per second or something like that. So be careful with units. And the hardest part, though, is when we have to convert between one another. So let's do a different example. So now we're going to look at the conservation of energy. So what the conservation of energy means is we can't create any new energy, right? All the energy that exists is going to stay the same throughout the entire scenario. So if we had a certain amount of energy at the start, and suppose it was just potential, when that object starts to move, our total energy still has to be the same all the way through. So we cannot create or destroy energy, we can only switch it from one form to the other, and whatever the change of energy that occurs, remember, is still our work. So let's do a simple example. So let's suppose we have a 2 kilogram object once again, and let's suppose it is 10 meters. Actually, let's just go with 5 meters. 5 meters above the ground, and we're going to release it. So at the top, our potential energy will be mgh, which we already did. So that's 2 times 9.81 times 5. So we get 98.1 joules. Okay, what is the kinetic at the top? It is going to be 0 because the object isn't moving. Before it drops, it's not moving. And then let's figure out what the potential will be at the bottom. So at the very bottom, our potential energy is going to be 0 because we have 0 height. Okay, so that means all of that energy that we started with has to then get converted all to kinetic. So we know that at the bottom, our kinetic energy will be the same as what we started with, which was 98.1. So our total at the top, 98.1, has to equal our total at the bottom, which is 98.1. So that means if we were somewhere halfway through, so if we were 2.5 meters down, that means half of the energy will be lost. So we'd actually have 49 newtons of potential, or 49 joules, and we'd also have 49 kinetic. So those two together would still add up to our 98 that we started with. Okay, so you get the idea that it's all we're doing is we're just taking from one to the other. But it's this concept that helps us solve a lot of questions. So let's suppose we wanted to know how fast it was moving at the bottom. So just before it hit the ground, it's going to have its maximum speed, right? As the object falls, it's going to speed up faster and faster and faster. We want to know how fast it's going at the bottom. So what we want to do is think of this as being our total potential at the start plus our total kinetic at the start will equal our potential at the end and our kinetic at the end. So you can use little prime or ticks to show that's before and after. So we already calculated that our potential at the start was 98.1, and we knew that we had no kinetic. And then at the end we have no potential, and we know our kinetic will be 1/2 mv squared. So we already knew that our total was 98.1, so we have 98.1 equal to 1/2 mv squared. So we can solve it for velocity because we knew our mass was 2. So our question then, our solution is just the square root, 98.1 divided by 1/2 times 2, which is just 1 anyway, so we'd have the square root of 98.1, which gives us 9.9. Okay, so quite a few questions you're going to get will be like this, where you're asked to find a velocity at the end or something like that to be able to solve for the question. So let's do a couple different examples. So let's do one where we have an object sliding down a ramp. So let's suppose it was already moving at 2 meters per second. So it's going down the ramp at 2 meters per second. And let's suppose it's 5 meters above the ground. And let's suppose it was 1 kilogram. So let's assume the question says, how fast at the bottom of the ramp if the ramp is frictionless. Okay, so in this case then we'd want to figure out our potential at the start, but we also have kinetic at the start because it was already moving at 2 meters per second, and that will equal our potential and kinetic at the end. So our potential at the start, mgh, so we'd have 1 kilogram times 9.81 times 5, so that gives us 49 joules. But this time we also have kinetic, so we need to figure out that. So 1/2 mv squared. So 1/2 times 1 times 2 squared. So that gives us 4, so that gives us 2. So we actually have 51 joules of energy total before. So now our energy at the end, once it's down at the ground, it's going to have zero potential. So that means all of that 51 newtons will get converted to 1/2 mv squared for kinetic. So we can actually solve it for velocity now. So our total at the beginning, the 49 potential, plus the 2 kinetic gave us 51. So now we can solve it for velocity. So we'd have 51 divided by 1/2 and square root that answer. And we get an answer of 10.1. Okay, so the only thing different about this question is that we have kinetic and potential at the beginning, so you got to make sure you add those two together. The ramp itself doesn't do anything, right? It would be no different if I asked this question of what was the 1 kilogram object if it just fell straight to the ground. It would be the exact same answer. That's assuming that the ramp is frictionless. So let's just modify this question a little bit. So let's suppose, I'll just jot it on a new page here. So let's suppose we have the exact same ramp, the exact same scenario. But now we know that at the bottom, its speed was only 1 meters per second. Or actually, let's do a different number. Let's say it was 1/2. So let's suppose the box started at 2 meters per second, and actually that's too small. Let's change it. Let's suppose, we already know from the last question it should be around 10. So let's suppose it ended up actually, in reality, going about 8. So in this case, what happens is our total potential plus kinetic has to equal our total potential and kinetic at the end. So we have, at the beginning, we have, let me just go back and look at the numbers again. We had 49 and 2. So we had a potential of 49, we had a kinetic of 2. We have a potential of 0 at the bottom, but now we know it's moving 8, so we can actually figure that out. So we'd have 1/2 mv squared, so we'd have 51 on the one side, and on the other side we'd have 1/2. Our mass was 1 kilogram, if I remember right. Yeah, 1 kilogram, and our velocity is 8 squared this time. So we'd actually have 8 times 8 is 64, times 1/2 is 32. So in this case, we started with 51 joules of energy, but now we know it's ending at a speed of 8, so that means it's only going to have 32 joules of energy at the bottom. Well, those things aren't equal, so what's the problem? So that means the energy that we started with, some energy was lost. What did it get lost to? And the answer is friction. So friction changed the energy. So what we can say is it did work, right? Remember, work was change of energy. So in this case, we'd have 51 minus 32, which means we have 19 joules of energy that was taken away from friction. So if you get questions where it says, how much work or how much energy did friction remove from the system, find your energy before, find your energy after, subtract the two, and in this case friction would be that change of energy. And that is it.